So I'm recording the lecture. Okay, so are there any questions before I start? Switch it to this side. Okay, so in the last class, we talked about the dual of the consumer's problem. So the usual consumer's problem is maximizing utility for a given budget, and that gives rise to Marshallian demand functions as the choice functions of that problem. And you have the indirect utility function, which is the value function of that problem. So we discussed what the dual of that problem is. The dual of that problem is the expenditure minimization problem. You have a utility target instead of a fixed income, and you have to minimize expenditure cost subject to reaching that utility target. Okay, so the dual problem is intimately connected with the original. And for the dual problem, the choice function that arises from the dual problem is called the Hicksian demand function. And the value function that arises is called the expenditure function. So the expenditure function specifically tells us it's a function of the prices and the utility target. It tells us for a given utility target and for a given set of market prices, what is a minimum amount of money which is needed for the consumer to reach that level of utility. So then we discussed some properties of the expenditure function. And one property, which is going to prove to be very important in what we're going to discuss today, is the concavity property. So the expenditure function, we can prove, is concave in prices. I also discussed at the end of the last lecture what concavity means. In mathematical terms, the more general definition is, involves those inequalities which I discussed. And if the function is twice differentiable, then we can also give an alternative calculus-based characterization of local concavity of a function, which involves the Hessian matrix. Okay, so now let me very quickly sketch the proof of why the expenditure function should be concave. And there we'll exploit the inequality-based definition. Yes, and the proof is very simple. So let's take two price vectors, P1 and P2. Remember, these are price vectors, so these are superscripts. So they're different price vectors. Now, when the prices are P1, there is some consumption bundle or vector which minimizes expenditure. Let's call that X superscript 1. And when the prices are P2, there's another bundle which achieves expenditure minimization. Let's call that X superscript 2. Okay, so remember the definitions. X1 is optimal when the prices are P1. X2 is optimal when the prices are P2. Now, let's take a linear combination of these two price vectors, P1 and P2. Let's call it X bar. Okay, let's call it P bar. Okay, so P bar is this lambda, 1 minus lambda weighted combination or average of P1 and P2. Now, there will be some other consumption bundle which will minimize expenditure for this averaged price vector. Okay, let's call that X bar, right? So X1 is optimal when prices are P1, X2 is optimal when prices are P2, and X bar is optimal when prices are P bar. Now, immediately, we can write down these two inequalities, okay? What is the first inequality saying? It's saying that when the price vector is P1, the bundle X1 costs less than the bundle X bar. That follows from the definition that X1 is supposed to be the optimal purchase when prices are P1, right? It minimizes expenditure. So that immediately implies that this weak inequality has to hold. Similarly, when the price vector is P2, this inequality again follows straight from definition. The bundle X2 should cost less than the bundle X bar when prices are P2. So now it's very simple. We can take the first inequality, multiply both sides by the scalar lambda. The inequality will be preserved. We can take the second inequality, multiply both sides by the scalar 1 minus lambda. Again, the inequality should be preserved. Then I can add up the left-hand sides and add up the right-hand sides. Again, that should preserve the inequality. And that gives us this line. Okay. Now, if you now look at this line, what's inside this bracket is nothing but the price vector P bar, the average price vector. Okay. So we end up with this inequality. And now if you look at this inequality, then we immediately can jump to the next step. What is P1 times X1? It is the value of the expenditure function when the price vector is P1, because X1 is the optimal choice. So whatever expenditure is involved in P1 X1, that is the value of the expenditure function by definition. Similarly, P2 X2 is the value of the expenditure function at P2. And P bar X bar is the value of the expenditure function at the price vector P bar. Okay, so we can write this next line. And this next line is the very definition of the concavity of a function. Okay, this is exactly how we defined, if you remember the discussion at the end of the last lecture, that if we average first and then put it into the function, we should get a higher value than if we put the two endpoints into the function and then do the averaging. That is the very definition of concave functions. And that definition is satisfied here for any arbitrary price vectors P1 and P2 we might start with. So that proves that the expenditure function is concave. Okay. Any questions? All right. Rachita, do you have a question?
Yes.
Rachita, if you don't have a question, please turn off your microphone.
Am I audible?
Yes, you're audible now. Yeah. What's your question? You're audible, Rachita. You were audible a moment ago. So just go ahead and speak. Seems like you're having audio problems. Okay, so let me put that on hold. Let me move forward. Okay, so now we are sort of arriving at our destination, so to speak. First, I'll talk about a very important result of this sort of classical choice theory or consumer theory called the Slutsky equation. The Slutsky equation addresses the issue of how demands change when the price of a good changes, how it affects the demand for that good and the demand for other goods, all of them. And what it does is that it decomposes the effect of a price change into two parts called substitution effect and income effect. Okay. Now, we'll try to understand, as with many of the key concepts, we'll try to understand it at three levels or from three angles. One is using the most powerful mathematical tools that we have, which we have developed and have been using. Second is diagrammatically, especially with a two commodity case. And the third is intuitively, all right, in plain English. So let's discuss all three perspectives and connect and tie them up together. Okay. So this is the Slutsky equation. What is it saying? First of all, in calculus terms, it's saying on On the left-hand side, you have del xi, del pj. All right. So that is exactly the object we are interested in here. What happens when the price of the jth good changes? Let's say it goes up slightly. What happens to the demand for the ith good? Now, that incorporates the special case where I equal to j. Okay, so in that case, we have the own price effect. In other cases, when the two goods are distinct, we are talking about the cross price effect. Okay, so the Slutsky equation is saying that this slope, this derivative of the ith demand function, consists of two parts. The first part is the corresponding slope of the Hicksian demand function. Remember, this is the Marshallian demand function. This is a demand function which arises from the utility maximization exercise of the consumer. And the Hicksian demand function is the demand function which arises from the expenditure minimization problem of the consumer, the dual of the utility maximization problem. So the slope of the Marshallian demand function, the first part of that is the slope of the Hicksian demand function. And the second part is this. This consists of the slope with respect to income times xj. Okay, so this part is called the substitution effect. This is called the income effect. I'll talk in a moment why they're called so. I need to break for 30 seconds to answer the door. Okay, sorry about that. So this is the equation.
So here xj as a function of p and y is basically the demand function of the good j, right?
The Marshallian demand function.
The Marshallian demand function. All right, sir. Thank you.
Yes. So all the slopes, well, not all the slopes. This one is for the Hicksian demand function. The other two are slopes of the Marshallian demand function. Okay, this is the equation. So first, I'll just show you the proof or sketch the proof for you. And then we'll go to the diagram and the intuition, and I'll link up the maths with that.
Sir?
Yes.
Sir, why are we seeing a cross effect here?
I'll come to that as I
sir.
go through the explanation. First,
Okay,
let's
sir.
just look at the maths of it. Okay. So we can prove it quite simply if we use duality relations. The proof, as you can see, kind of fits in a single slide. There are sort of longer ways of proving it, which you may have seen. I presume you haven't seen the duality-based proof in your undergraduate. Anyway, let's see how it goes. Okay, so we'll start initially with this identity. This I discussed before, if you recall, in a previous slide. What is this saying? It is saying that let's start with some given utility level, U, right? That's some number, some fixed number. Let's calculate the value of the expenditure function at that utility level. That tells us what is the minimum amount of money which will enable a consumer to reach that utility level. Okay. So at that utility level, if we solve the expenditure minimization problem, we'll get the value of the Hickson demand function. So that's on the left-hand side. Now, if we take that utility level, calculate the minimized expenditure, give exactly that amount of money to the consumer, and calculate the Marshall lane demand function, it will match, right? Remember that the consumer's original problem and its dual problem has the same tangency solution, right? Both problems achieve their respective optima at the same point of tangency. That's where this equivalence or identity comes from. Okay, so since we have this identity, we can equate, let's differentiate with respect to Pj. That's the parameter change that we are talking about here. So we'll take that derivative on both sides and equate them because it's an identity. So on the left-hand side, we simply get the slope of the Hickson demand function. On the right-hand side, when we are differentiating with respect to Pj, notice that Pj affects the Marshallian demand function here through two routes or through two channels. One is that it directly affects it, okay? And the other is that it affects the expenditure function, and a change in the value of the expenditure function, and so the income available, creates a further change in the value of the right-hand side. Okay, so that's where the two terms come from. First, Pj has a direct effect, which is this component, del xi del Pj. And then it also affects this function through its second argument. And there, if we apply chain rule, we have del E del Pj, right? Change in the second argument of the function, times del xi del y, essentially, right? This is the derivative of our Marshallian demand function with respect to its second argument, which is income, expenditure, whatever you want to call it. So that's this part. All right. So this is straightforward rules of differentiation. Now, now the last trick is all of these are helpful. The last thing sitting here is the slope of our expenditure function with respect to Pj. Okay, nothing like this appears in the Slutsky equation, right? So somehow we have to transform this and write it as something else. Now there we can fall back on Shepard's lemma. Remember what Shepard's lemma says? It says that the slope of the expenditure function is basically, you know, with respect to the jth price, gives us essentially the demand for the jth good, xj. So I'll replace this derivative by xj. And xj meaning the Hickson demand function, right? Because the expenditure function arises out of the expenditure minimization problem, the dual problem. So the relevant demand there is the Hickson one. So we replace this by xjh. Now, xjh, this is the perils from lecturing from home. Just one moment. Okay. So yeah. So then the last thing we'll exploit is this equivalence between the Hicksian and the Marshall-Lindemann function. And this again utilizes the fact that this U and this Y are conjugate pairs, right? If we set this utility target, this Y is the amount of money which is needed. If we give this amount of money, then U is the utility that can be generated, okay? And again, using the fact that the two problems, the consumer's problem and its dual, gives us the same tangency solution. From that, we can substitute this value of the Hicks-Lindemann function evaluated at U with the value of the Marshall-Lindemann function evaluated at Y. Okay, so once we do that substitution, we get the Slutsky equation. So the proof is done. Okay, so that's just the mathematics of it. Right now, it's somewhat opaque. So let's try to understand this more.
Sir?
Yes.
So in the Shepard's lemma line, it's just the same as the duality, right? The identity.
No.
We're going from Hickson demand to Marshall demand.
This part is Shepard's lemma. Okay.
Yes.
Then the next part is duality. Yeah. So it's a combination of Shepard's lemma and duality.
So the right hand side is an identity. The other, the latter part is an identity. Okay, sir.
That's right. Yeah. Okay. Now, let's keep this in our hands. All right. Let's shift gears and move to the picture, the diagram for the two goods case. Well, let me postpone that just for a little while. Let me actually talk about the next slide, and then I'll come back to the diagram. So as I've been saying for a while now, we want to tease out the testable implications of this sort of rational choice theory. What are the predictions it makes, which can be checked against observable data? Okay, if we collect a large volume of data, for different price vectors, what are the different choices of the consumer for different prices, incomes, etc., etc. And if we put it together, does this theory tell us about some pattern we should see in that sort of data? And what are those testable implications? Okay. It's a second matter whether they actually are borne out by the data, whether the data supports the theory. But first we have to understand what is the theory saying about what patterns we should see in the data. So that's what this slide is about. Okay, so these are the three testable implications. The first two are relatively innocuous. Really, the meat of it is contained in the third bullet point. So I'll come to that. First, the first prediction is budget balancedness, and that's coming from strict monotonicity. This is basically saying all the income will be spent on all the goods. This is kind of trivial. In reality, of course, people save. But if you consider saving as one of the goods that we consume, it's like we are consuming future consumption. Then, you know, budget balance is kind of, it's almost circular that it will be satisfied. So let's move on from that. A second prediction is homogeneity of degree 0. This is saying that if prices and income all go up by the same proportion lambda, it should not change the demands for the various goods. Yes. And this follows straight from the fact that the budget set or the budget line does not move at all if everything is multiplied by the same factor. If all prices double and also incomes double, then is the same choice set that the consumer faces. And so she shouldn't change her choice. The optimal choice remains the same. One sort of implication of this is, of course, that if there's uniform inflation in an economy, literally every price goes up. Okay, that means everybody's income has also gone up by the same factor. Right? This is kind of the macroeconomic national income identity sort of idea that every transaction is a price for someone and an income for somebody else. Yes, if you go to the market and buy vegetables, you're paying a price, you're the consumer, but on the other side of the transaction is a seller for whom what he paid is an income. Okay, so saying that literally all prices in the economy have doubled means that all incomes have also doubled. So if that happens, that is like uniform inflation, literally uniform inflation. That doesn't change anything. People continue to buy the same things that they were buying before. Everybody has the same utility as before. So but we worry about inflation, of course. The newspapers are full of articles when the consumer price index is going up at a high rate. There's a lot of discussion. So why is that? That's because in the real world, inflation is rarely uniform. Okay, so inflation creates redistribution. Some prices go up more than others. And so some people actually gain from inflation and some people lose out. What is a typical example of a group who gains from inflation? Borrowers, right? And lenders lose out, because most loan contracts are not inflation indexed. They're fixed in nominal terms. So borrowers lose out. People, with fixed income, like retirees, for example, right? Unless the interest rate also increases at the same rate as goods and services, leaving the real rate of interest unchanged, unless that happens, then retirees on fixed income, they lose out, and so on. There may be other costs of inflation. For example, there may be deadweight losses that arise if people anticipate inflation. So for example, you were planning to buy a car, but the right moment for you to buy a car is when you start a new job, let's say 6 months from now, and move to a new city, and so on. But if you think there'll be very high rates of inflation over the next 6 months, you may buy your car too early, and that's a kind of distortion that inflation induces. Anyway, the first order effect of inflation is really neutral. Yes, it is costly because of all these other factors, that not all prices are going up uniformly, or people are making distorted choices to beat the inflation, and so on. But let me come to the main point, which is this point. What is this saying? This is saying that this matrix, what is this matrix? This matrix is the matrix of all the first derivatives of all the Hicksian demand functions. The first row is all the derivatives with respect to prices of all the Hicksian demand function for the first good. The second row is for the second good, and the last row is for the nth good. Okay, so this is saying that this matrix is what is called negative semi-definite, meaning its principal minors alternate in sign, starting with negative. So the first thing here is negative. Then this 2 by 2 matrix and its determinant will be positive. And the 3 by 3 will be negative, and so on.
So this is independent of the nature of cross price elasticity, right? Between the two goods. So this is independent of what the sign of del X1 by del P2 will be.
That's right.
All right, sir.
So how is this symmetric?
This is symmetric. I'll tell you. Okay.
So what is the significance of this particular matrix?
Well, it depends on. I'm telling you, I'm not jumping ship here. I'll explain things, and then whatever is unclear, you can clarify with me. So first of all, what is this matrix? I've defined what the matrix is, right? Let's just focus here and not let our eyes stray elsewhere right now. So there's a matrix of all the slopes of the Hickson demand function. So it's saying that, some of these determinants have to have particular sign, as I just said. And also it's symmetric, which means, this is the cross price effect, the effect of a change in price of good 2 on good 1, the Hickson demand for good 1. And this is the mirror image of that. This is the cross price effect of a change in price of good 1 on the Hickson demand for good 2. So these two have to be equal. That's what symmetric means. Yeah.
So can you repeat the symmetric bit, please?
Symmetric means that if you take the ijth element of this matrix, it has the same value as the jith element.
Why would that be?
I'll tell you.
Oh, okay. Okay. Right, sir.
Yeah.
So could you repeat the signs of the principal minors, like from positive, negative, positive, negative, or is it the reverse?
It's negative and then positive.
Okay, sir. Thank you.
Yeah. Okay, so first let me explain why this claim. Okay, and then we'll talk about what this claim implies, why am I selling it as a testable implication of the theory. So why is this claim true? Okay, to see that, let's do a rewrite. Okay, remember Shepard's lemma. What is Shepard's lemma telling us? Shepard's lemma is telling us that every Hickson demand function, say for the ith good, is basically a slope of the expenditure function with respect to the ith price. So take a close look at it again, have it in your head. And now if I go back and look at this matrix that we were just talking about, let's take this term, for example, del x1, del p2, okay, del x1h, Hickson. Now, x1h itself is the derivative of the expenditure function with respect to p1, okay? So this term is a second derivative of the expenditure function, therefore, right? x1 itself is a first derivative. And which second derivative is it? It is del square e, del p1, del p2. Okay, and every element of this matrix can be converted to a second derivative of the expenditure function using Shepard's lemma, right? So that's what I've done here. The ijth element of this matrix is nothing but del square e, del pi, del pj, right? Derivative with respect to ith price and the jth price. Everybody see that? This is a straightforward application of Shepard's lemma. That's why we discussed Shepard's lemma and proved it and listed it previously. Now, another property of the expenditure function that we talked about and which I proved at the beginning of today's lecture is that it's concave, right? And as I discussed yesterday, if a function is concave and it's a differentiable function, the calculus definition or characterization is that it's Hessian matrix. What is a Hessian matrix? It's the matrix of all the second derivatives, right? So this matrix is the Hessian matrix of the expenditure function, right? And since the expenditure function is concave, that means that the Hessian matrix has this property that it's principal minus alternating sign, negative, positive, negative, and so on. Okay, so that's where it comes from. This matrix is the same as the Hessian matrix of the expenditure function. The expenditure function being concave, it has its principal minus alternating in sign, and therefore this matrix also has to have that property, and that's the basis of the claim. Okay, now here's the thing. Look at the title of this slide. It's the testable implications. Yes. Now, this matrix contains terms which involve the Hickson demand function. The Hickson demand function is not observable. Out there, consumers are not solving that dual problem of expenditure minimization, except in rare cases when, you know, we are talking of some kind of aid given by some NGO or a government to put some household at some minimum level of utility. Except in those cases, in the real world, the consumers are solving utility maximization subject to a given budget, subject to a given income. So what we observe in the real world are not Hickson demand functions, but which kind of function? Marshallian demand.
Marshallian demands.
That's what's observable. Okay, so this is a swindle. I've been a snake oil salesman. I have tried to sell you some testable implications, but I am marketing a testable implication which involves things which are not observable from the data. So have I been involved in false marketing? Where is the catch?
Sir, Hickson demand function is identical to Marshallian due to the duality, hence their derivatives become similar.
Due to yeah, duality is involved, but there's a result. There's a very important result we talked about today itself.
Slutsky equation.
It's the Slutsky equation, right? Yeah. The slope of the Hickson demand function del xi h del pj, thanks to the Slutsky equation, can be written as del xi del pj plus this term. You take it to the other side, right? So both of these two other terms are properties of the Marshallian demand function, which we do observe. Okay, so I can rewrite this this matrix substituting the Hickson demand functions by Marshallian demand functions appropriately. Of course, you know, every term will then be the term that is that the Slutsky equation tells us. So it will consist of two things: this slope del xi del pj plus xj times del xi del y. I can do that substitution in this matrix, and then the matrix becomes a matrix of entirely observable elements. And since we are saying something very precise, we are actually making statements which can be tested against data. Okay, Ganesh.
Sir, in the Marshallian demand function, we have y as the parameters, income as the parameter. So how we are able to observe each individual's income when we are saying that Marshallian demands are observable?
In principle, okay, this is
from like revealed preference theory sort of thing.
No. In principle, you can do household surveys and collect data on people's incomes, right? In practice, if you look at NSS surveys, for example, we get consumption data, but there are surveys where household income is estimated from the survey. We are at the mountaintop of theory. Okay, so we'll be happy if we get testable implications, which are in principle testable, and sometimes we get rich enough data sets where we get tested, right? In a country like India, household incomes are often, it's notoriously hard to estimate. That is a practical difficulty, of course. But in more advanced economies like the US, you have data sets where household incomes are included, and a few data sets in India too.
And sir, when we are saying that Hickson demand is not observable, we are saying that because of that fixed utility term, that's
right. I mean, what is the real world correspondence of a Hickson demand function?
Okay, sir.
Right. The problem which most consumers are actually solving is that they have some money and they are buying food and clothing and housing and entertainment and so on.
Okay, thank you.
Ria.
So when you said that these individual components of the Hessian matrix are independent of the cross price elasticity, does it mean that we're going to ignore the signs? We're going to just take the modulus of these derivatives?
Are independent of the signs. I didn't say that.
Independent of the cross price elasticity, like someone asked.
The symmetry. You're talking about the fact that this is symmetric. This is a symmetric matrix. That's what you're referring to?
Yes, sir.
Okay, so let me, I forgot to talk about that. So let's go back to the fact that this matrix is also the Hessian matrix of the expenditure function. So it consists of every term is a cross-partial derivative. Now, what do we know from calculus? If you take a function and differentiate it twice with respect to two arguments, does the order of differentiation matter?
No, sir. The cross partials are equal.
So it's called Young's theorem, right? It doesn't matter in which order you're taking the derivative. So del square E del Pi del Pj is the same as del square E del Pj del Pi, okay? So this matrix, the matrix of the second derivative of the expenditure function, is a symmetric matrix because of Young's theorem. Yes, and since this matrix is also is basically the same matrix, that means this is also a symmetric matrix, which means that these cross price effects have to be equal, right? So it's not immediately obvious if I write it in this form, but using the results that we are using, namely, Shepard's lemma, Slutsky equation, etc. We can see why this has to be a symmetric thing. And so that's another testable implication, that the effect on the demand for these cross price effects have to be the same. Yeah. Nandini? Nandini, you have a question?
Yes, sir.
Yeah.
So actually, I got everything, but here we are discuss about properties of Marshallian demand. Then why we take into account this Hickson demand? I don't get this. What is the role of this? If we are talking about Marshallian demand properties.
Okay, for a moment, forget about Marshallian demand functions, right? Whatever is written here is true. I gave you the reasoning and the logic. Yes?
Okay, sir.
Are you convinced about whatever is written here? Namely, that this matrix is negative semi-definite and symmetric.
Yes, sir.
Okay. Now let's come to the question. The elements of this matrix involve the Hickson demand function, and you're right to complain about that, right? Because it's useless. We don't observe Hickson demand functions, even in principle. Even if you give me all the data in the world about consumers, I won't be able to observe it. So it's not useful to me. But this is why we bothered to talk about the Slutsky equation. The Slutsky equation gives us a relationship between these derivatives of the Hickson demand function and the derivatives of the Marshallian demand function. right? So as a last step, what we can do is we can do that substitution using the Slutsky equation. Yes, I can take this derivative of the Hickson demand function and I can write it as del xi del pj plus xj times del xi del y. So I can express this thing as the sum of two slopes of the Marshallian demand function. So now if I go back to the matrix, I'm allowed to do that substitution. I can substitute every element, which is a slope of Hickson demand function, by the sum of two slopes of Marshallian demand, the corresponding Marshallian demand function. So after that substitution, the property of this matrix, namely that it's symmetric negative semi-definite, does not change. Okay, so we arrive at a step where we have been able to say something about properties of the Marshallian demand function. Okay.
Yes,
So
sir.
there are many moving parts. You have to wrap your head around all these moving parts. Yes, but the final step where we arrive is something very useful. It is a statement about what properties the Marshallian demand function ought to have, and those statements can be checked against data, whether they hold up or not. I'll explain things further, right? There's discussion left here. Quickly, Pratibha.
Sir, can you explain this negative semi-definite property once?
Negative semi-definite just means that the principal minors alternate in sign, right? So the first principal minor, essentially this element, ought to be negative. Then the next 2 by 2 matrix ought to be positive or weakly positive. Then the 3 by 3 ought to be negative, and so on.
And so what's the implication of this?
I'm coming to that. I'm coming to that. Yeah. Let me proceed a little further, and then I'll take more questions. All right. Okay. Now let's zone in on one subset of the implication of this symmetric negative semi-definiteness. Suddenly, this element, right? Look at the diagonals. The diagonals, let me switch back to talking in terms of Hickson demand functions. Keep in mind that whatever we are saying about Hickson demand functions here has a corresponding description in terms of Marshallian demand functions, thanks to the Slutsky equation. Okay, but having said that, I'll talk in terms of these things. So what are the diagonal elements? The diagonal elements are the own price effects on Hickson demand functions, right? Every diagonal element is, the second one says if the price of the second good changes, what is the effect on the Hickson demand function of that good itself? Similarly, the third and the fourth and so on. So all of these are own price effects on Hickson demand. Now, it's easy to see that one implication of this entire bullet point is that all of these diagonal elements have to be negative. The first one is negative is straightforward from the very definition, because it's the first principal minor. The others have to be negative too. Okay. For example, if you calculate the second principal minor, you will have the product of these two minus the product of these two. Now the product of these two is a square, right? It's a minus squared thing because it's symmetric. They have the same value. Okay. So if I calculate the 2 by 2, the determinant of this 2 by 2 matrix, the second principal minor, I get this product minus something has to be positive. So obviously the first term, the product of this first diagonal and the second diagonal element have to be positive, right? Now, this one is negative, this one has to be negative too to make the whole product positive. Okay, so you can extend the reasoning to argue that every diagonal element has to be negative. Okay, so that means that the Hickson demand functions satisfy the law of demand. Okay.
So here I have a question.
I'm coming to that. Just hold on just a moment. Yeah, I'll
Okay.
take questions. So we reached the conclusion that, let's say, for good I, del need to activate this somehow. Just a second. Oh, okay, I'll say it in words. Let's go back to, okay, let's focus on own price effects. All right. This is negative. Okay. The Hickson demand function has a negative slope with respect to its own price. But what we're really interested in is the slope of the Marshallian demand function. We want to know whether this will always be negative. Okay, this thing. Now, you can see from the equation that that's not guaranteed. So, for example, if this term, del xi, del y, is a negative number and large negative number, then for the equation to hold, this will have to be positive. Right now, I'm just being somewhat mechanical and just focusing on the maths. I'll link it up to everything else. But if you focus on the Slutsky equation, so far we have proved that, you know, the right-hand side over here is negative, but that does not guarantee that, you know, this is negative, because if the second term is a large negative number, this could end up being positive. Okay. However, one thing we can say, if the second term is a positive number, if del xi, del y is a positive number, then this has to be negative for this equality to hold, because on the right-hand side, we have a negative number. Okay. So this is saying that, okay, what does del xi, del y mean? Being positive means? That means it's a normal good. Its income elasticity is positive. Okay. So for those goods which have positive income elasticity, whose demand goes up when consumers get richer, for those goods, the law of demand has to hold them. Even the Marshallian demand function has to be downward sloping. That's something we get by looking at this equation, Slutsky equation, very closely. However, in some cases, the law of demand may be violated. We may have positively sloped Marshallian demand curves, but there is a condition, a necessary condition for that. Such goods which violate the law of demand, they should have negative income elasticity, meaning they ought to be inferior goods. It's necessary that they are inferior goods. Only inferior goods may end up violating the law of demand. All inferior goods won't, but some inferior goods may violate the law of demand. But all normal goods satisfy the law of demand. That's something we end up here. So goods which violate the law of demand are called Giffen goods, right? So what we see in this slide is the possibility of Giffen goods. Okay, Giffen goods are compatible with consumers who choose rationally and have well-behaved preferences. Okay, they can have theoretically positively sloped Marshallian demand functions. All right, so now having done the math and the most general sort of treatment, I will link this to the usual diagrams and intuitive ideas. So, well, let me finish that. Let me, let me demand a little more patience from you guys before I take questions. So let me go back to the kind of picture which many of you will be familiar with from the undergraduate. Let's focus on the two commodity world. Okay, there are two goods. Oh God. Oof. I need to restart my. Just a second, guys. Okay. Can you guys hear me? Am I audible?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
For some reason, my writing pad isn't working. So I need to close this. Let me restart it. Okay, we're back in business. So, Too Good World. Where X2, X1. So there's an initial set of prices. So let's say this is the budget line. And there's a point of tangency. Let's call that point A. So these are the demands for the two goods. Okay, this is X1 prime, this is X2 prime. So now, oops. Now suppose P1 goes up, good one becomes more expensive. All right. So we'll have a new budget line which swivels in. Okay, everybody familiar with that? This is our new budget line. P1 has increased. So we have to find the new point of tangency. Let's say it's something like this. Let's call it point B. And it corresponds to different levels of X1 double prime. This is X2 double prime. Already I'm in trouble with the picture. I haven't drawn it very well, but I'll try my best. Okay, let's do a following thought exercise. As the price of this good has gone up, obviously the choice set of the consumer has shrunk, and so the consumer will be worse off, no doubt, right? The green indifference curve is lower than the red indifference curve, so the consumer has become worse off. Let's say the government, becomes very worried about this, and the government says, "Oh, we'll pay some cash compensation to this consumer, to this household, so that they get back to the old utility level," right? Market prices are what they are. This good is more expensive now. What can we do about it? But let's give some extra money to these guys, right? Just a lump sum cash transfer, so that they can get back on the red indifference curve. So as you start giving out cash to the household, what happens to this budget line?
It shifts out parallelly.
Moves out in a parallel fashion, right? And so if you want to do this compensation, you have to push it out enough so that it goes back and becomes tangent again to the old indifference curve, the red indifference curve, right? You have to hit this point of tangency. Now it's pretty clear, because the indifference curve is convex, right? This point of tangency, after we start pushing out the new budget line through cash compensation, that the new point of tangency that will hit will not be the A, but it'll be some point like C, which is further up the indifference curve, right? To the left and upwards. Okay, let's focus on the point C. The point C corresponds to some quantity x1 triple prime, let's call it, and x2 triple prime. All right. Now, in diagrammatic terms, we can now identify the income and the substitution effect. This movement from A to C captures what is called the substitution effect. Okay, so on the x-axis, on the horizontal axis, this change is the substitution effect.
Sir, is point C on the same IC?
Yes, that's what I just said, right? We
Okay.
are pushing out the budget line so that it just goes and just about hits the old indifference curve. Yes. And that's our point C. So the movement from A to C captures the substitution effect. Okay, so for the first good, this is the substitution effect. For the second good, there will be a corresponding substitution effect, which I'm not labeling. And the movement from C to B is what is called the income effect. All right. Now, let's first match it up with the maths of it. Remember, in the Slutsky equation, how do we capture the substitution effect? What did we call the substitution effect? It's the slope of the Hickson demand function that we call the substitution effect. You remember that, right? So, on the picture, why is this thing called the substitution effect? Because it's nothing but the slope of the Hickson demand function. Hickson demand function comes from where? We are doing an exercise of adjusting x1, x2, all the quantities, so that the consumer remains at some fixed utility level U. That is where the Hickson demand functions come from. Hickson demand functions are obtained by fixing the indifference curve or fixing the utility level at some constant number. And so the movement from A to C is exactly that. It's movement along the same indifference curve as the price ratio changes. So naturally, this part of the diagram corresponds exactly to the slope of the Hickson demand function. Of course, here we are not taking infinitesimal things. We are taking finite changes. That's just an approximation to explain things. But the movement from A to C is really what corresponds to slopes of Hickson demand functions. And then if you look at the movement from C to B, okay, these are parallel budget lines. C arises from some budget line and B arises from another budget line, which is a parallel shift of that. Okay, so the movement from this budget line to that budget line essentially is a change in income. So the movement from C to B captures a change in income. And that's why it's called the income effect. And in the maths, it shows up as a derivative of the demand function with respect to income. Okay, so that's the link between our picture and the mathematical derivation, which I did, and hopefully you can see it more or less clearly. So A to C is our substitution effect, C to B is our income effect. Okay, now, what is the intuitive meaning of all this, or how do we understand this? You know, when something becomes more expensive, there's an obvious reason why we should want to buy less of it. You know, it's just more expensive. But then what it also does is that, you know, if one of the things we buy, especially if it's something that we spend a lot of a budget on, like, you know, our rents or food or something, then the price increase also reduces our real income, so to speak. We are poorer. And in terms of the picture, that is captured by the fact that our budget set has shrunk, right? The consumer now has access to a smaller set of consumption bundles. So that's like a change in income. And the change in income will have an additional effect on how much the consumer buys. And that's the income effect, okay? So what are giffen goods? Giffen goods come from, you know, the historical reference is an economist, Irish economist, Robert Giffen, towards the beginning of the 20th century, if I remember, did a study of the demand for potatoes in Ireland. And the claim is, and this is somewhat controversial, you know, those days the econometrics wasn't that sophisticated, so they didn't do all kinds of controls. But anyway, the claim from that study is that Giffen found that in periods when potatoes were more expensive, Irish households bought and consumed more potatoes. So the demand for function for potatoes seem to have the perverse slope. Now, we can understand why that is the case and why that might happen, because it was a very poor country, Ireland, at the time, right? Ireland has had an economic miracle in the last 20, 30 years, but it was also very severely hit by the financial crisis of 2008. Anyway, but for the most of the 20th century, it was one of the poorest countries of certainly of Western Europe. So these were very poor people. And you can imagine the following kind of scenario. Okay, there's a poor household. 6 days a week, they eat bread and potatoes. They cannot afford luxury items like meat, for example. But they save up a little bit for 6 days. And on Sunday, with their weekly savings, they go and, you know, they go to church, they come back home, it's a holiday. So they sit down for a nice meal where they have meat. Okay. And now potatoes have become more expensive. So they don't manage to accumulate the savings over the 6 days, right? Most of their money is spent buying bread and potatoes. So come Sunday, they don't have enough money to buy meat anymore, but they have to eat on Sunday. So what do they eat? They eat potatoes again. So that's how you may have this phenomenon arising, right? And if you think about that story, the reason it's happening is because potatoes are an inferior good. When they're short of money, they fall back more on potatoes and cut back on meat. And that is the effect that is kicking in to generate a giffen good.
So this should hold true also in the converse case, right? When the price of potato is falling, its consumption should fall.
That's exactly right. Yeah.
So could you just give us a scenario where this is happening? I'm not able to understand how exactly this decision is being made.
In terms of the story which I just sketched?
Yes, sir, in terms of your story.
Okay, I mean, it's very easy, right? I mean, so now potatoes suddenly become very cheap. So now Friday itself, they have enough savings to buy potatoes for the weekend, to buy meat for the entire weekend, Saturday and Sunday, right? So then they take advantage of that and have meat on Saturday and Sunday. And so in spite of becoming cheaper, potatoes, they don't buy potatoes on Saturday anymore. And so their demand for potatoes has come down.
So basically, they reduce their consumption a little more to be able to buy more meat.
That's right.
Got it, sir.
Yeah. Okay, so let me take questions then. Yeah. Nandini. Nandini, you have a question? Okay, let's move on. Let me move on to Kanishk. Kanishk, what's your question?
So, sir, in the Hessian matrix, del xih upon del pi is negative. How are we claiming that? Sir, in the matrix form.
Just a moment. I'll just stop it here.